Hello, everybody, and welcome back to another visual pattern challenge. Here's our pattern today. Here's step one, here's step two, here's step three. And your challenge, and it's a tricky one today, is to predict the number of squares in step four. If you can manage that, a much more difficult challenge would be to predict the number of squares in step 43. This is not easy. And along the way, can you write an equation that could be used to express the number of squares in any step at all? So that's the challenge. If you'd like to accept it, pause the video and see how far you can get. All right, I think this is a particularly difficult pattern to sort out, partly because the way the blocks are arranged don't give us very many clues about what's really going on here. I guess since in step one we see this diagonal, I'm going to think about diagonals. And here we just have a diagonal of 3. And then in the next step, it looks like we've got 3 diagonals. So we've got a middle diagonal, and that's 4 long this time, and then diagonals of 3 on either side. And then let's see, in the next step, yeah, we've got an even longer diagonal in the middle. That's a 5 this time. And then we've got the diagonals of 4 and 3 on both sides. Okay, so that makes sense as a pattern. So that middle diagonal gets 1 longer, and then we kind of repeat the decreasing diagonals on either side. So if this middle diagonal in step 3 was 5, I think in step 4 it should be 6, and then we'd have a 5 and a 4 and a 3 on that side, and then a 5 and a 4 and a 3 on that side. So I think that's what step 4 should look like. And let's see, what does that add up to? That's 7, 12, 18, and then I think that's 30. So it looks like 30 blocks in step 4. Okay, I think we've gotten to step 4. Let's see what we can do in terms of analyzing the numbers to get some ideas about this pattern. What do you think before we start analyzing the numbers? Does this look linear to you? Does it look quadratic? Do you think it could be something else possibly? For me, when I look at this, I see things growing in 2 dimensions at once. So these diagonals are getting longer, and then there's more diagonals on the sides. So I'm thinking quadratic, but could be something else, but that's my hunch. So let's analyze these numbers. So we'll put the step number and the number of squares and see what we get. So in step 1, there are 3. In step 2, let's see, that's 4 and 3, 3 is 10. And in step 3, then that is 19, I think. And in step 4, we're predicting 30. And then we can take the differences in each step. So 10 minus 3 is 7, 19 minus 10 is 9, and 30 minus 19 is 11. So we didn't get a constant there, so it's not linear. And then we take the differences again. 9 minus 7 is 2, 11 minus 9 is 2. So we do get a constant in the second order differences, in the difference of the differences. That means it's a quadratic pattern. So x squared is going to be our leading term. And because this is 2, I know the coefficient of that leading term is 1. So that at least gives me a starting point. Now, oftentimes a strategy, once you know you have a quadratic and you know what the coefficient is, would be to sort of block that out and see what's left over. I think that's pretty difficult in this case. So I'm going to actually try a different strategy. I'm going to make another chart and just write these numbers differently. So what I'm going to do for each step is just write the total expressed in the number squared, because I know I have this x squared there, and then whatever's left over. So this would be 1 squared plus 2, and 2, that would be, 2 squared plus, so that's 4 plus 6, okay? And then this would be 3, that's 3 squared, so 9 plus 10 then, and this would be 4 squared, that's 16 plus 14. Okay, so it may not look at first glance that this has helped us much, but now I can look at these leftovers, and think about how to express them. So 2, that would be the step number plus 1, or 2 of the step number, but 6, the step number, well, it's not the step number plus 2, and it's not the step 2 of the step numbers. Another way to think about this is to think about the differences here. So 2 to 6 is 4, 10 minus 6 is 4, 14 minus 10 is 4. So this chunk of it is going up by 4 every time. So I could think of this as 4 times the step number plus or minus something. And looking at step 1 is going to give me a good clue there. So 4 times the step number would be 4, but I only need 2 more. So I'd actually have to subtract 2 there. So 4x minus 2 for this little chunk, let's see if that works for step 2. That would be 4 times 2 minus 2, that'd be 8 minus 2 is 6. Aha. And this one, 4 times 3, that'd be 12 minus 2 is 10. And 16 minus 2 is 14. Yeah, so this little chunk right here can be expressed with this. So that was tricky and hard to get to. The whole thing now should be this and this together. So the equation I'm going to propose here is y equals x squared plus 4x minus 2. Now there may have been another way to get to that equation. So if you have come up with a different way to get there, I'd love to hear about it. But let's double check that this one actually works. So here would be 1 squared plus 4 times 1 minus 2. That's 1 plus 4 minus 2. Yeah, that's 3. And here it'd be 2 squared plus 4 times 2 minus 2. That's 4 plus 8. 12 minus 2 is 10. Yes. Let's just try it here too, just to make doubly sure. So 3 squared plus 4 times 3 minus 2. That would be 9 plus 12 minus 2. So yeah, that's 19. So this equation does seem to be working. Now, to calculate the number in 43, we just have to put in 43 for x. So y equals 43 squared plus 4 times 43 minus 2. And let's see here, 43 squared is 1849, and 4 times 43, that'd be 4 times 40 is 160, plus 4 times 3 is 12, 172, and that would be 2021. And then we subtract 2 from it. So I'm getting 2,019 squares in step 43. So I think this was a super difficult one. How did it go for you? Were you able to get step 4? I think even that's a little bit tricky. And how did it go with coming up with an equation for this? I would love to hear about it. Thanks, everybody.